Dear students, welcome to this online class on IR spectroscopy. In this class, we will discuss the application of IR spectroscopy on various molecules. When we try to interpret the IR spectrum of a molecule, we should have a clear idea about the basic IR frequency values of various functional groups. Some important base values are, as given in the table, you can see OH and NH have got the highest value of around 3500 or 400 centimeter inverse. Remember, IR frequency is expressed in wave number. Then CH bond stretching frequency is around 3000. C triple bond N and C triple bond C comes around 2100 or 200. C double bond O, that's carbonyl group, which is the most important functional group, giving most intense peak in IR spectrum, that is having the value 1715. C double bond C, which comes in alkenes and aromatic rings, you get a stretching frequency of 1650. And C single bond O, that it comes around 1100. Only the important values are shown here. And this table shows a relative place of each functional groups. Remember, the IR absorption frequency ranges from 667 to 4000 centimeter inverse. You can see various functionalities coming at various places. Remember that the IR frequency depends on, it's based on this equation, nu bar is equal to 1 by 2 pi c root of k by mu, right? This is the equation to calculate the frequency of IR radiation absorbed for the vibrational transition by a molecule. And here you can see this frequency depends on k as well as mu, where k is the force constant, which is an index of the bond strength. Mu is called reduced mass, which is roughly a measure of the atomic mass of the bonded atoms. So frequency depends upon two factors. So it's not easy to predict where the frequency comes. Now, before we go into the examples, you should note an important point regarding IR spectrum, that is what is known as fingerprint region. What is it? In the IR spectrum, I told you it ranges from between 667 or roughly 700 to 4000. Now the region from between 700 to 1400, okay, that region is known as fingerprint region. Why is it called so? Because this region has the characteristic that it consists of a large number of peaks. Maximum number of IR peaks are obtained or seen in this range. Why? It is because of stretching vibrations of C single bond C, C single bond N, C single bond O, right? Which are all very weak bonds. The weaker the bond, smaller the frequency, and also it is most of the bending vibrations also comes in these regions. So due to that, a large number of peaks are seen in this region. And the important aspect of this region is that this part of the spectrum of a molecule is so characteristic of a compound of the molecule that it is used to identify the compound, okay, or it is the fingerprint of the compound. to detect, to identify a compound, you can easily check this fingerprint region part of the spectrum. That means similar molecules may have very similar spectra outside this region, but fingerprint region makes the difference. See, look, for example, this is the spectrum of ethanol. You can see that most of the peaks are coming over here. This is the part that is the fingerprint region. And in ethanol, the most important characteristic peak is that of OH, which comes outside this. It is here around 3400. So if you take ethanol and methanol and compare, the IR spectrum of both the molecule will be very similar outside this fingerprint region, but fingerprint will be very different, or it is unique. You can easily distinguish ethanol and methanol looking at the fingerprint region. That is why it is called fingerprint region. And also you see various IR spectrum of various molecules which we have to discuss. Look at this phenol. You can see maximum number of peaks comes here in this region. There is a fingerprint region. Similarly, look at all this. You can see most of the peaks are coming in this fingerprint region between 700 to 1400. Okay. Now let us go to the example starting from alcohols. In alcohols we discussed that of ethanol. See, when you get the IR spectrum of a molecule, what is important is you should be able to identify the characteristic peaks or distinguishing peaks of a molecule. Even without seeing the spectrum, you should be able to predict what are the characteristic peaks of a molecule. For example, here ethanol, you know, the structure of ethanol is CH3, CH2OH. It is already, you can see in the below the spectrum. So the most characteristic IR peak is the OH peak, right? And what is the value? You should be able to predict the approximate value of IR frequency. You know, it is around 3400 centimeter inverse. Okay, centimeter inverse. So this is that peak, and you can see it's very broad. Why? See, the value sometimes it comes down 3400 to, it may comes to 3200 also, due to hydrogen bonding. We have discussed it in the previous class, and it is broad because of this hydrogen bonding only. And in ethanol there is, the next is CH stretching frequency, which comes around 300. Actually below 300 it may be something around 2850, like that, because it is aliphatic or sp3 carbon. So CH stretching frequency of aliphatic carbon comes below 3000. And there will be also CH2 bending frequency around 1450, 1375 extra. That's all not very significant, not very intense. But there is another important peak for alcohol is, that is C single bond O. That is also there, you know, in any alcohol, and that comes around 1100 centimeter inverse. So these are the most important distinguishing peaks of alcohol, any alcohol. Okay, next we take phenol. See, when you compare alcohol and phenol, here also there is OH, and the value comes again around, so the OH frequency, you can see OH frequency comes around 3400. Due to hydrogen bonding it will be coming below 3400, comes to nearly 3200, etc. And there will be C single bond O around 1100. This is around 3200, etc. This comes around 1100, like that. And in phenol you will have aromatic CH stretching, that's very important. CH stretching frequency of aromatic carbon or aromatic CH bond, which will have a value above 3000, so it comes like 3050 like that. Okay, it comes above because CH bond is stronger in the case of aromatic compound. So these are the important characterizing IR peaks for phenol, right? Okay, now next we have amines, we have aniline. Here the most characterizing IR peak is that of amino group, that is NH2. Okay, so NH stretching frequency comes around again, just like alcohol, it comes around 3400. Here also due to hydrogen bond it will come lower, and this is primary amine. There are two NH bonds, and which will show a kind of doublet. You can see in the spectrum, you can see a kind of doublet here. Okay, so that is the speciality of a primary amine. And another characterizing peak of amine is C single bond N will be there, which is not very significant, anyway noticeable. It comes again just around 1100. And finally there is aromatic CH stretching, right? Okay, that comes just above 3000 centimeter inverse. Okay, one more point regarding aromatic compound, that also comes in the case of aniline. Remember, in the case of aniline also we should note that in the case of aniline, not aniline, phenol also, for any aromatic system, there is there will be carbon-carbon double bond, right, in the ring, and that will show very characterizing peaks at 1600 as well as 1475. Two peaks you will get for aromatic CC stretching. The same thing comes in the case of aniline also. There will be aromatic CC stretching. Okay, C double bond C stretching at two. You will have two peaks, one at 1600, another at 1475. There will be slight difference in the values anyway from compound to compound, right? And sometimes one peak may get masked by another if they are very close. That also happens. We go now to ether, and this example is dibutylether. See, the IR spectrum of ether is not very interesting because it has only one characteristic functionality, that is C single bond O, right? Only that, and that comes around again 1100 centimeter inverse. See, we are supposed to know only approximate value, roughly where this peaks comes, not exact value. That varies from compound to compound. Okay, and in addition to this CO, definitely there will be, for any aliphatic compound, there will be CH stretching coming just below 3000, and also that means it will be around 2850 or so. And there will be also, there are so many CH2 groups which will show bending vibrations at 1450 as well as 1375. This is a characteristic IR frequency for CH2 bending vibrations, right? Now we move on to the next functional group, that is aldehyde. Here it is butanal. You know the structure of butanal. Okay, so what is the most important peaks? In the case of carbonyl compounds, the most important peak is that of CO, that is a carbonyl group, which is most intense. You can see this is the one, and it comes around 1715. Okay, and in addition, for aldehyde, there will be a CH stretching peak for the aldehyde CH. See, it is not the aliphatic CH. The CH of CHO group is very characteristic, and it gives two peaks, one at nearly 2800 and another at 2700. Two peaks are given by aldehyde. This is very characteristic of aldehydes, and this is how we distinguish aldehyde from ketone, because ketone also will give carbonyl peak at 1715 around, but this CH of aldehyde is given only by aldehyde. In addition, it will have, as usual, the CH touching frequency of aliphatic carbon, sp3 carbon, and there will be CH bending frequency as well. Next we go on to benzaldehyde, this aromatic aldehyde. See, here again you have the most important peak is that of the aldehyde, the carbonyl group. See here, an interesting point is that since this CO group is in conjugation with benzene ring, right? This is in conjugation with the ring. The CO, due to resonance, the CO bond will become weak and frequency will come down to around 1700 centimeter inverse. That is a speciality of aromatic aldehyde. And as before, it will have CH stretching of aldehyde group. Two peaks we will have, and there will be CH stretching of the aromatic hydrogen. There will be CC stretching of the aromatic CC bond. Okay, all these will be there as usual. The next is ketone. We take butanone, butan 2-on as the example. You know the structure of butan 2-on, CH3, C double bond O, CH2, CH3. Okay, what is the most important IR peak for this compound? Definitely the most intense peak, that of carbonyl group CO, were around 1715 centimeter inverse. And after that there is only CH stretching of sp3 carbon around 2850, and also there will be CH2 bending vibrations, bending frequency obtained at around 1450 as well as 1375. And then next we take aromatic ketone. See, here also the most distinguishing peak is that of the carbonyl group, just like in the case of benzaldehyde. Here also, due to conjugation with the ring, the CO frequency will be lowered to around 1700 centimeter inverse. And then as usual there will be aromatic CH stretching around 3050, just above 3000. There will be CC stretching due to aromatic ring at 1600 and 1475. See that there is a CH3 also connected to CO group, so that will also give the CH stretching due to the sp3 carbon just below 3000 also. Now we have the next one, benzoic acid, that's a carboxylic acid. See here, in the case of carboxylic acid, you will have of course the OH peak will be there, and it is hydrogen bonded, so it is very broad, you can see here, and it comes a little lower. See, it comes even below 3000. Why? Because you know benzoic acid is having extensive hydrogen bonding, it is having very strong hydrogen bonding. Due to that it comes even below 3000. See, it is much lowered. Okay, and then the next important peak is that of the carbonyl group, and it comes around 1720 like that, 1720 or 25 like that. And of course there will be CO at around 1100, and there will be, since aromatic, there will be okay, since it is aromatic, okay, it is this one. Since it is aromatic, it will have this CH stretching, okay, of aromatic, right? Okay, so these are the important peaks for acetophenone. Oh, sorry, benzoic acid we are discussing, right? So here, since there is benzene ring, it will have this CH stretching of aromatic hydrogen just above 3000, and there will be also C double bond C stretching of the aromatic ring at around 1600 and 1475 centimeter inverse. Next, we have the next one, an ester. This is ethyl acetate. Okay, what about ester? What are the characterizing peaks in ester? See, of course, the most important one will be the CO group. It is there, right? For ester, see that CO bond is strengthened due to the OR group. We have discussed in the previous class. So it comes a little higher, like 1740, like that, because CO bond is stronger here. And you have a very intense peak that is here. It is 1752 is shown it here. Of course, it varies slightly. Then there will be CO peak at 1100 around. And after that, it's only CH stretching of sp3 carbon or aliphatic carbon just below 3000 or like 2850 like that. And finally, there will be CH2 bending around 1450, 1375 like that. So these are the various peaks for ester. And finally, we have amide. This is acetamide. You know the structure of acetamide. CH3, CO, NH2. This is acetamide. Okay. So what are the characterizing peaks? Of course, just like amines, this is NH2 group is there, so it will show NH frequency, and you can see it's something like a doublet, right? Split into two, because primary amine has two NH bonds, so it will give two peaks, and that is around 3400 or even lower because of hydrogen bonding. It may come around 3200 or so. So that is one NHP, NH stretching frequency. Then comes CO, of course, it is very intense. Remember, in the case of amide, CO frequency is lowered, even it comes below 1700 also because of resonance. Because the lone pair on, see, the lone pair on nitrogen will be in conjugation with this CO group. So the CO bond get single bond character, or I mean it become longer or it become weaker and frequency is lowered. Then what else? There will be C single bond N peak also in the case of amine, and that again just like CO, it is also around 1100. See, this will be there for amines also. C single bond N stretching frequency comes around 1100. And finally, there will be CH stretching of aliphatic carbon at around 2850. And finally, CH2 bending frequency around 1450 and 1375. See, don't worry about these values and all. What you are supposed to know is the base values. You should have a clear picture. And when you are given a molecule, okay, when you are given a molecule, and you should draw the structure and predict what are the characterizing IR peaks, which are the functionality, and what is the estimate value. You should be able to distinguish between two compounds like aldehyde and ketone. How can you differentiate like that? Okay, that's all in IR spectroscopy. Thank you.